Have you ever flipped a light switch and just stopped for a second to wonder? I mean, how did a power plant, maybe hundreds of miles away, know in that exact instant to make just a little bit more electricity just for you? It really feels like magic, doesn't it? But it's not. It's actually something way more interesting. A constant, high-speed, invisible dance. Okay, let's dive into this.
Just think about it for a second. Millions of us were turning on TVs, charging our phones, firing up massive factories, all at totally different, unpredictable times. The demand for electricity is just this constant, chaotic roar of consumption, and yet somehow the system almost never fails.
Because here's the thing. On the other side of that equation, the supply, the amount of electricity being generated, has to match that chaotic demand perfectly, and it has to do it in real time. If there's not enough power, the whole system collapses into a blackout. If there's too much, equipment could literally be destroyed. This isn't a problem that gets solved every hour or even every minute. No, this balance has to be kept second by second.
So how does the grid know if it's in balance? Well, it listens to its own heartbeat. That heartbeat is the grid frequency. Here in North America, that beat is a steady 60 times per second, or 60 hertz. In Europe and other places, it's 50 hertz. If demand suddenly shoots up, that heartbeat slows down, just a tiny, tiny bit. If demand drops, it speeds up. This frequency, it's the single most important vital sign of the entire grid's health.
So in this explainer, we're going to pull back the curtain on this incredible balancing act. We'll meet the automated guardians of the grid, we'll uncover the clever trick that lets them all work together without even talking to each other, and we'll see how it all comes together in this beautiful, unseen electrical dance.
All right, so the most important thing to realize is that this system has to be automatic. There is absolutely no time for a person to sit at a control panel and react. Instead, the grid relies on two incredibly fast, automated guardians.
And here they are, the ALFC and the AVR. Now the AVR, the automatic voltage regulator, that handles voltage stability. Super important, but a story for another day. Our focus is on its partner, the ALFC, the automatic load frequency control. This is the system that watches the grid's heartbeat, that frequency we were talking about, and controls the real power output of the generators to keep that heartbeat steady. And what's so cool is seeing how they work in parallel. You can see here the AVR loop on the bottom is managing voltage, but look at that top loop. That's our guy, the ALFC. It senses the frequency, and its whole job is to control the turbine, the engine that's actually making the power. So let's follow that signal and see where it goes.
We're going to follow that ALFC signal right inside the control loop. Let's see exactly what happens the moment you decide to turn on your air conditioner on a hot day.
It's this beautiful, lightning-fast chain reaction. The instant the demand goes up, the massive rotating weight of all the generators on the grid slows down just a little. That causes the frequency to drop. A device called a governor instantly detects this tiny change in speed, and in response, it physically opens a valve to let more steam or water into the turbine, making it spin faster, generate more power, and push that frequency right back where it belongs. The whole thing, it takes just a few seconds.
And this right here, this is the core of that system, a classic mechanical speed governor. Now, I know it looks kind of old-fashioned, but the principle behind it is pure genius. As that turbine shaft spins, centrifugal force pushes those little weighted flyballs outwards. If the turbine slows down, gravity pulls the balls back in. It's a completely physical, mechanical way to measure speed.
Now that little movement from the fly balls is tiny, right? So it gets passed through a series of levers to something called a hydraulic amplifier. This thing uses high-pressure fluid to turn that tiny little movement into a force strong enough to move the absolutely massive steam or water valves that control the whole turbine. And finally, you've got a speed changer, which lets the human operators fine-tune the target speed they're aiming for.
Okay, so that makes sense for how one generator can respond to a change in load. But our grid isn't just one generator. It's hundreds, all connected, all spinning in perfect, synchronized lockstep. And that, well, that introduces a massive coordination problem.
Seriously, how do they all decide who picks up the slack? If a million homes suddenly turn on their lights, does one giant power plant just handle it all, or do they all chip in? And if they all chip in, how do they know how much power to add without some central supercomputer telling every single one of them exactly what to do second by second?
The answer lies right here in this graph, and honestly, it is one of the most clever things in all of engineering. Instead of designing a governor that tries to perfectly hold the frequency at exactly 60 Hz, engineers intentionally build in a flaw. It's called droop. Just look at the graph. As the power output goes up, the governor is designed to let the frequency drop by a small, predictable amount.
And this is the part you really gotta get. This droop isn't a bug. It is the single most important feature that allows for the stable, decentralized control of the entire power grid. It's the secret sauce. It's what lets hundreds of generators dance together in perfect harmony without ever stepping on each other's toes. So how does this intentional little flaw solve our giant coordination problem? Well, it all comes down to that simple downward sloping line.
Okay, let's watch this in action with two generators on the same grid. They're humming along at frequency F0. Now, boom, the total load on the grid increases. The frequency for the whole system starts to drop. Both governors sense this drop and start opening their valves. The frequency settles at a new, slightly lower level, F1. But look at what just happened. By dropping to that new common frequency, Generator 1 automatically ramped up its output by delta P1, and Generator 2 automatically ramped up its output by delta P2.
Think about that. No central computer was needed. There were no phone calls or frantic messages between the power plants. Simply by sharing a common frequency and each having its own preset droop characteristic, they automatically and perfectly shared the new load. Generators with a steeper line, a higher droop setting, take on a smaller share of the load, and those with a flatter line take on more. It's an elegant, emergent form of coordination.
So let's zoom back out now and put all of these amazing pieces together to see the full, beautiful dance that happens every single time you use electricity.
And this diagram just ties it all together in a neat bow. A change in the load causes a change in frequency. The droop characteristic, which is built right into the governor, senses that frequency change. That tells the turbine to adjust its power, which then feeds back into the grid to stabilize the frequency. It's this continuous, elegant, self-correcting feedback loop that keeps our lights on.
You know, in a way, it's helpful to stop thinking of the grid as just a machine and start thinking of it more like a living thing. A vast, dynamic superorganism with hundreds of hearts all beating in perfect unison, constantly sensing and responding to maintain a perfect, delicate equilibrium. It's a system built on incredibly simple, local rules that create this amazingly complex and stable global behavior.
But here's the final thought. This elegant dance was choreographed for a very specific kind of dancer. Big, heavy, spinning generators. As we move to a grid with way more solar and wind, which don't have that physical spinning inertia, and new kinds of demands like millions of electric vehicles, the fundamental dynamics of the grid are changing. So the question we have to ask is, how will this century-old, decentralized dance have to learn new steps to keep the lights on for the future?